Pre-calculus students, welcome to your 11.3 notes. We're going to take a look today at the tangent line problem. Really big topic in calculus. We're at the beginning stages of it. It builds on the other topics that we've looked at through this chapter on how we use limits. So let's get right into it. What we want to find when we're finding limits is essentially we're finding what's called a derivative. We'll get into that later, but the key to that is it gives us the slope of a line that's tangent to a graph at a specific point. Essentially, you could start by thinking of it as like an eyeball test kind of thing. So if I look at this example number one here, and I might say, okay, so what's the slope of this line? Well, okay, so here's the curve, and we're looking for the line that's tangent through this point, 2 and 2, and I see this line right here. And when I look at it, it looks to me like the slope is up. It's a little less than a slope of 1. I would say it's probably about a slope of 1/2. So essentially what we're doing is we're trying to be a little more precise with that type of calculation. But that's really all there is to it. What's the slope of the line that's tangent? But we're going to be a little more specific. Now, here's the reason we care about this, or maybe more specifically, how we approximate this. So if you imagine this purple line that I'm dragging around here, we could find the slope of this purple line by doing something like this: the change in the y value divided by the change in x. And if you look at this diagram we have here, the change in y value is essentially the difference between f of x plus h and f of x. So if I take f of x plus h minus f of x, that tells me my change in y, where the change in x would be represented by x plus h minus x, or as you know, it's just a movement of h spaces, and it looks like this. Now, the idea is I want that gap h to get smaller and smaller and smaller because I want to be able to actually calculate at the tangent effectively when h is 0. When there's only one point I'm finding the slope between instead of having to pick 2. And so that graph would look something like this. So by finding the slope of this line, I've effectively found the slope of the tangent line to that point. Again, that's just coming from what you hopefully recognize to be the difference quotient. Now, we use different notations to represent this calculation. As I mentioned a moment ago, we call it the derivative. You'll see it written multiple ways, but I would say probably the most common would be these first two. And then probably in third place would be this one right here, the d f of x dx, or you might hear people say d dx of f of x. This last notation over here, d sub x of y, is probably the least used, but you might bump into it at some point down the road. But I would definitely make sure you're familiar with the first two, dy dx, and then f prime of x. These are both ways of saying the derivative. So at times we're going to use the derivative to find just a general equation that would represent the slope anywhere, but sometimes you can use that difference quotient to find the slope of the tangent line at a specific point. So the first two, we're going to do that, where we just find the slope at one specific point. So again, we will use the difference quotient. It's the limit as h approaches 0 of, now in this case we're going to say instead of f of x plus h, we know that x is 3, so we're going to say f of 3 plus h minus f of 3 over h. Again, that comes from knowing we're using the point 3 and 10, so we're calling that point right there x. Alright, so let's go ahead and evaluate this. Now, one thing we'd need to be careful of is make sure that you appropriately plug in the h plus 3 or 3 plus h, whichever order you want to think about it. But when we do the f of 3 plus h, that would be 3 plus h quantity squared plus 1. And then we do minus f of 3. Well, we already know f of 3. It was given to us. F of 3 is 10. And then that whole thing, of course, is still divided by h. All right, so we need to do some simplification. So we'll have the limit as h approaches 0 of 9 plus 6h plus h squared plus 1 minus 10. And you might notice we have 9 plus 1 minus 10. Those are going to be all gone, so say goodbye to the constant values. All right. And the other thing you'll notice in the numerator, notice how both terms have an h. So I'm just going to rewrite it this way. I'm going to divide everything by h. It's the limit as h approaches 0 of 6 plus h. Now, again, what I've done is I've just divided both these terms by h. Okay, we're ready to apply our limit, and all of a sudden this problem just became a whole lot simpler, didn't it? That's 6. And what that means is that our slope at the point 3 and 10 is exactly 6. All right, we're going to do the next one as well, similar fashion. We have a radical, it's negative, so we have a couple little complicating factors here, but it's the same kind of idea. So we'll be looking for the limit as h approaches 0 of f of x plus h. Now, in this case, though, x we're saying is negative 1, so we'll say negative 1 plus h minus f of negative 1 all over h. So again, we have to make sure we plug things in accurately. So here we go, limit as h approaches 0. F of negative 1 plus h would be negative square root. Now instead of x, we're doing negative 1 plus h, and then plus 2, minus f of 1, well, or f of negative 1. And we actually know f of negative 1. It's given to us as negative 1, so I'm just going to change that to a plus 1 right there. And the whole thing is over h. Now you may have realized we're going to have to do a little bit of simplification here. Now, if I switch the order of these, actually no, I'm going to do a little simplification first before I deal with the conjugate. I think that might help make sense. So the limit as h approaches 0, and I'm going to reverse the order of the numerator and make it 1 minus the square root of, and then I'm going to go ahead and change that to h plus 1 at the same time, over h. Now we'll go ahead and deal with the conjugate. All right, so I'm going to multiply this by 1 plus the square root of h plus 1. So what I'm doing here, of course, is trying to rationalize the numerator. This is one of our techniques we learned earlier this chapter that allows us to simplify and to evaluate limits when otherwise we wouldn't be able to. So here we go, the limit as h approaches 0 of, and then my numerator would be 1 minus the quantity of h plus 1. My denominator, well, the denominator is a little bit ugly, but that's okay. It's h times the quantity of 1 plus the square root h plus 1. Now, if you're paying attention here, you're going to see pretty quickly, like, okay, so in the numerator, we have 1 minus 1. Those are gone, so all that's really left is a negative h, and that's divided by h. So realistically, what we have here is the limit as h approaches 0 of negative 1 divided by 1 plus the square root of h plus 1. Folks, at this point we can go ahead and evaluate our limit. So we can plug in 0 for h. Negative 1 divided by 1 plus 1 would be negative 1/2. That means the slope of this graph at the point negative 1 is exactly equal to negative 1/2. All right, as we move forward, I have a little secret to tell you. The method that we used on numbers 2 and 3, I hate it. It's really annoying to me. I don't like plugging in a negative 1 or f of negative 1, any of those things. I much prefer what we're going to do on number 4 or 5 or basically any other problem, which is find the derivative and then plug in the points. To me, it just makes more sense. It's possible somebody disagrees with me, but that's okay. Every once in a while, other people are wrong. So I'm just teasing, all right? I'm teasing. All right, so here we go. So f of x plus h is what I want to find because I'm going to be finding, again, the general derivative, which comes from that difference quotient. So we're going to have x cubed. Let me rephrase that. X plus h quantity cubed, which we know would be x to the third plus 3x squared h plus 3xh squared plus h to the third. These numbers come from the Pascal's triangle, right? So 1, 3, 3, 1. And so here we go. That's f of x plus h. This is f of x. Let's evaluate this. So the limit as h approaches 0 of f of x plus h, that's what we just found, x cubed plus 3x squared h plus 3x h squared plus h cubed minus f of x, which is x cubed, all divided by h. And again, we run into what we've run into many other times. Anything that doesn't have an h is going away. So there we go. And let's divide everything by h as well. So we have the limit as h approaches 0 of 3x squared, I'll put that in parentheses to distinguish that, plus 3x h plus h squared. And folks, at this point we can just simply plug in our limit as h approaches 0. So we'll do that. As h approaches 0, this is going to become, well, that term's going to be 0, that term's going to be 0. All we're left with is 3x squared. Okay, so right there, that is in fact the derivative. And I'm going to write it as such. I'm going to write f prime of x is equal to 3x squared. Now we can use that. So let's find let's see, it says to find a formula for the slope of f and use it, we just found the formula by the way, and use it to find the slope at the given points. So f prime of -1 would be 3 times -1 squared. So the slope there is 3 times 1, or just simply 3. And we could do the same thing with the derivative of f evaluated at 2 would be 3 times 2 squared. So that's 3 times 4, which is 12. All right, so these are our slopes. This is our derivative. Pretty cool stuff. It is, I promise. You'll see. Just give it some time. It'll start to soak in how powerful this is. All right, let's take a look at number 5. It's really the same instructions as 4, same kind of idea, just a little bit different algebra hoops to jump through. So we're going to do the limit as h approaches 0. Now in this case, f of x plus h is just simply 1 over x plus h minus 3. Then we would subtract the function f of x, and don't forget to leave a little space to divide by h. All right, so here we go. Again, common denominator. We've run into this problem a lot throughout this chapter and other times. We're going all the way back to about 4th grade probably. Add or subtract, get a common denominator. So here we go, x minus 3 minus, and I'll put this in parentheses, x plus h minus 3 over, and then the common denominator in this case would be x plus h minus 3 times x minus 3. And there is that h down here to divide the whole thing by. I'm going to move it right there. If you have questions on how I can get away with doing that, talk to me and I'll show you. It's a pretty simple little shortcut that might save you a little time. All right, our x's, goodbye, 3's, -3 minus -3, that's the same as plus, right? See you later. And once again, we are left with just simply the terms that have an h, and in this case that's only one of them. It's a negative h divided by h, so we have the limit as h approaches 0 of -1 over x plus h minus 3 times x minus 3, and we're ready to apply that limit. We can plug in 0 for h right now, and we'll have -1 times, well, if you get rid of the h, that's x minus 3, and it's times x minus 3, so I'm going to write it as x minus 3 squared. So what we have right there, of course, is our derivative. I'm going to write it this way, dy dx, squeezing that in on the side there. There's our derivative, -1 over x minus 3 squared. Now again, we have 2 points to evaluate it, and so we'll evaluate at both of those points. I'll start with the 2, -1 point. I'm going to show you this. It's going to be the same thing I did on the last one. It'll just look a little different with notation. But 2 minus 3 quantity squared is what we would have. And so that's 1. So our slope here is -1. That's our slope at 2, -1. We also need to check at -2 and -1/5. you probably have noted that the y values aren't really that important to us on this kind of problem. We're much more interested in x. So we'll have negative 1 over, let's see, negative 2 minus 3 quantity squared. That's negative 1 over, well, negative 5 squared would be negative 1/25. That's the slope at the point negative 2 and negative 1/5. So again, the three things we were looking for, there's the derivative, which you might call the general equation for the slope of the tangent line. There's the slope at negative 1, and there's the slope at negative 2. As we move to the next problem, I actually want you to pause the video. I want you to find the derivative on number 6 on your own. Find the derivative and then compare your answer to mine. Now I hope you paused that video, and if so, welcome back and you can see my work. Essentially I found f of x plus h, and then I did f of x plus h minus f of x, again our difference quotient. And what happened was the x squared term and the 5x terms canceled out. The three that were left, I divided them each by h. I got 2x plus h plus 5. And at that point I was ready to apply the limit of h approaching 0. And that left me with simply 2x plus 5. Pretty cool stuff. Now, if I wanted to go further and find the slope at any particular point, I could easily do that. Just plug in the x value and it's done. All right, let's walk through number 7 together. We'll have I'm going to start by finding f of x plus h. Even though there's not a lot of work we can do on this one, I'm going to go ahead and write it here just to remind myself. There's f of x plus h. So I'm going to find the limit as h approaches 0 of f of x plus h, which is going to be x plus h plus 5 minus f of x all over h. And again, we're going to have to use conjugates, our good friend conjugates, back to help us out again. And so here we go. It's a little bit ugly this time, but square root of x plus h plus 5 plus square root of x plus 5. We're going to do that numerator and denominator, just like we always do. X plus h plus 5 plus square root of x plus 5. All right. So when we do the multiplication here, the reason we like those conjugates is they allow us to get rid of some radical symbols or some square root signs in that numerator. So we'll have x plus h plus 5 and then minus x and minus 5 because they're both subtracted. And then the denominator, as we're used to seeing, or at least we hopefully are used to seeing because we've seen it a lot now, the denominator ends up being, fairly messy. But that's okay because we still have some more canceling work to do. Like, I see that I have an x minus x and I have a 5 minus 5. And what do you know? I have an h divided by an h. That's just going to give me a 1, right? So what I really have here is the limit as h approaches 0 of 1 over the square root of x plus h plus 5 plus the square root of x plus 5. And at this point we can apply our limit and we'd get our solution. It's 1 over, and we'd have the square root of x plus 5 plus the square root of x plus 5. That's two of them, just like, x plus x is 2x. Well, the square root of x plus 5 plus the square root of x plus 5 is 2 square root of x plus 5. And that is our derivative. Pretty cool. As we move forward here, why don't you pause the video and do number 8 on your own. Yeah, go ahead. Just do number 8 on your own. Welcome back. Now, I hope you didn't spend a ton of time on number 8. If you did, sorry, sort of. But you'll see I actually just kind of jumped right to the answer. If you scroll back on your notes, look at the other side and look at number 5, you might notice a pretty strong similarity in that it's actually the same problem, just with slightly different directions. So I don't feel like redoing that all over again. If you did, that's good practice for you. If not, you can go look and see yours on number 5 and you'll see what we did then. All right, so let's move forward to the next one, number 9. Find the slope of f at the given point. and then find the equation for the line tangent to the graph at the point. And then we'll also sketch the graph and the tangent line. That's a lot of directions. So here's what I'm going to start with. I'm actually going to find the derivative of the function. Now I know you could use the derivative at this specific point. As I've mentioned before, I prefer just to find the general derivative. So I'm going to do that. So here we go. The derivative would be the limit as h approaches 0. And the algebra might get a little messy on this one, just cautioning you. Leave a little space. And we'll have f of x plus h, which would be 2x plus 2h plus 1 minus f of x, so square root of 2x plus 1, all over h. Now you probably know what I'm going to tell you to do next because we've done this quite a few times. Use the conjugate. So here we go, the square root of 2x plus 2h plus 1 and plus the square root of 2x plus 1 all over the same exact thing. Definitely could have left myself a little more space. That's all right. I'm looking ahead and I have a pretty good idea that this space up here isn't going to be used for our graph anyway. All right, so now we know what we need to multiply. Let's go ahead and make that happen. So this is the limit as h approaches 0 of, we'll have 2x plus 2h plus 1 minus 2x minus 1 all over h, and then again the denominator that we love, square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. I feel like a bit of a broken record on some of this. We've seen this many times already. 2x's will cancel, 1's will cancel, and even the h's will cancel. Now that we only have a 2h in the numerator. And so we can see what we'd have here. I'm going to go ahead and apply the limit. It's going to be 2 over 2 of those square root of 2x plus 1's, and you may notice pretty quickly that we could just change that to 1 over the square root of 2x plus 1. All right, so we've done something. We found the derivative. Congrats to us. Now let's actually follow the instructions and finish the job. It says to find the slope at the given point. So at 4, 3, f prime of 4 would be 1 over 2, the square root of 2 times 4 plus 1. So that would be 1/3. And that's the slope at the point 4 and 3, 1, 2, 3, 4, and 1, 2, 3. I mean, technically right now I could go ahead and graph the tangent line, even though I don't even have the graph on here yet, but there's really no reason I'd have to have the graph to graph the tangent line, so hey, why not? There's the tangent line. Slope of 1/3 goes through that point 4, 3. All right, great. We want to sketch the graph and the tangent line. I'm ahead of them on sketching the graph, but or the tangent line, I should say, but we do need to sketch the graph. So let's sketch that graph. Now remember, we're going back to the original equation here, the square root of 2x plus 1. I'm just going to make a little t-chart, and we want to be pretty selective with our values in this particular instance because it could get ugly if we try to just pick random points. So for the square root of 2x plus 1, the first point I like to choose is -1/2 because that's exactly 0. The next point I like is 0 because the square root of 1, of course, is 1. And then I need to pick one more, and if I want to get a perfect square, probably 4 would be the best place to go because then I'd have 8 plus 1. So there it is, 4 and 3. Oh, 4 and 3. Yeah, that should be a point. All right. We had a pretty good clue for that one. So -1/2, 0, 0, 1, 4, 3. And we know it's a square root graph, and it's going to look something like this. A little rough on the graph, but you get the idea. And you can see that the line is, in fact, tangent. All right, I've actually skipped one thing, haven't I? It says to find not only the slope of the tangent line, but to also find the equation. So I'm going to step back for a moment and find the equation of the tangent line. And actually, we have all we need, don't we? I wrote that sloppily, but we know the slope is 1/3. We know it goes through the point 4 and 3. So how about this? Y minus 3 equals 1/3 times x minus 4. There's my equation. That's how it gets done. And we're now on to the problem you've all been looking for, the last one. So here it is. Find the derivative and use it to determine any points where the tangent line is horizontal. All right, so why don't you go ahead and pause the video and find the derivative for f of x. Pause it. Yeah, pause it now. All right, welcome back. You can see my work on finding the derivative of f of x. F of x plus h was fairly lengthy because you had to square x plus h, you had to multiply it by 4. So all this stuff here, don't forget you got to subtract the full f of x original function. But the nice thing is, just like we've seen so many times, a lot of those terms cancel out. And what we're left with, each one of them has at least one h. And when we factor that out and divide, you get something that's a lot simpler. And there's the derivative. All right, now there's one additional step here. It says determine any points where the tangent line is horizontal. Now here's where we have to think about this for a moment. Horizontal, what does that mean? Well, horizontal lines have a slope of exactly 0. And this is what's so cool. One of the things that's so cool about derivatives is now that I know the derivative is 2x plus 4, if I say 2x plus 4 equals 0, and real quickly you'll see x equals -2. That tells me some really interesting information. That tells me that at the point -2, and then we'd have to plug it into the original function to get the other part of that, but when we plug it in here we get 4 minus 8 minus 2, which is -6. So that tells me at the point -2, -6, I have a slope of 0. The tangent line's horizontal. You know what's amazing about that? That point is either a minimum or a maximum. We just had a brand new way to find a minimum or maximum value. This could be pretty powerful, especially when we're going to higher degree polynomials, to be able to do something like this. Yeah, it's awesome, isn't it? Your mind's blown. Right now, you are having a happy moment in your mathematical learning. I hope this has been a good lesson for you. I know it has been for me. So we'll see you at class. Come ready to work and bring your questions with you.